Okay, good afternoon, everybody. Have we got good audio at the back? Can you hear me, guys, at the back? So you haven't fallen asleep yet? Give me half an hour, you'll be fast asleep. I hope not. Only joking. Okay. I'm from the UK, I'm from England, and hopefully I'm going to give you a little bit of insight into the sort of the RF, the actual radio, the wireless side of the Microtik products, what's actually being radiated and some of the problems you might have. So where have I come from? At vast government expense, I was trained and worked in the UK government on various wireless projects and gained my skills from that, and then eventually at the prime age of about 45 years of age, the government decided they didn't want to pay out such large amounts of money for radio engineers anymore. They were way too expensive, so they got rid of a whole load of us in a mass redundancy plan, which paid off my mortgage on my house, so thank you very much for all your taxes that you've paid to pay off my house for me. Thank you. But then I got involved in doing consultancy and doing training because all that knowledge and experience that got inside my head, I wanted to pass that on. I'm not someone who believes in keeping it all to myself. I think it's more important that we pass this information on in this trade. Certainly the black art of wireless is something that can be very much of a mystery because it's difficult to see. I'm talking about difficult to see, I can't even see my own laptop. Okay. One of the other things is I'm a member of a sort of like a little mini exclusive club of Microtik consultants on a website called rootedworld.com, where you can see some of the really big major projects that we've been involved in all the way around the world. So go and have a look at the website, and I think that one of my colleagues in the team will be talking about that on another talk. Okay, I'm now currently working for a Microtik distributor in the UK called LinITX. I know it looks like it says Linitix, but it isn't, it's LinITX. We are the largest Microtik distributor in the United Kingdom. We have the largest number of Microtik consultants, and we provide quite a lot of support. Third line support, even in some cases first line support for wireless ISPs and also the more traditional ISPs who are using now the latest ranges of cloud core routers in their data centers for shifting quite large amounts of gigabits of traffic. Multiple peers with BGP all running on cloud core routers without any issues at all at a substantially reduced price compared to other vendors. So that's our business, that's where we've come from. Why am I here today? Teach you a little bit about wireless. So I'll finish the sales, straight into wireless. It's not something that you can see. If it's certainly a high enough transmitter power, you can feel it. But normally you can't see it, it's invisible. You need some tools to actually help you to work out what's going on. You may have point-to-point links, point-to-multipoint links that are failing, causing you high levels of CCQ, creating errors. And you can't immediately understand why this is the case. You may have changed frequency, thinking, oh, it's an interference problem. There's possibly someone on the same channel as me. I'll move the frequency to somewhere else. What tools do you use? And you might be using the snooper tool, wireless scanning tools. You might be using the Dude with its spectrum analyzer. Very, very powerful built-in function, totally provided free with the product. That might guide you to a quieter frequency, but you're still getting errors. You've still got poor CCQ. So what you might then think about doing is you climb the tower, you change the equipment for a brand new piece of kit, and the problem goes away. And the products are such low cost that you throw that in the bin, you throw that in the trash can, your problems are finished, you go on to the next problem after that. But as a distributor, we do get some of these products returned back to us on RMA. Fortunately, Microtik has a very, very low RMA rate. We find they're very reliable, but the cards that we do get come back, I get to have a little play with them when I've got some spare time, and it's very illuminating as to what's actually physically happened to them when they have failed. The part of the wireless card that is working the hardest and is generating the most amount of heat is the transmitter. When they get hot, they will eventually fail. That's the one thing about electronics. We know it is guaranteed absolutely that at some point in time in the future, it will fail. Now all we have to figure out is the precise moment when it will fail. That is a lot more difficult. So we know it's going to fail, and when it does, we get them come back to us, possibly because it's still under warranty, and then we go and have a look, find out what's gone on. So I've got some nice pretty pictures of what we've discovered. If you want to do this for yourself, you might actually use the free tools that are provided by Microtik, like the built-in spectrum analyzer tool in the Dude, which is very, very good. You might use some expensive equipment from HP and from Rohde & Schwarz, which is what we do. Or you might go for some more of the lower cost independent third-party solutions that can provide you with some quite good tools at a very low cost. The benefit of using the Microtik built-in spectrum analyzer in Router OS is you are actually using the real link itself. You're actually looking down the antenna bore, you're looking down the shot of where that antenna is looking. So you are now beamed on where your problems may be coming from. So it's a very, very good way of figuring out what's going on with a link. But obviously you need the Dude, and you need then to run the spectrum analyzer view. Quick hands up, how many people are using the Dudes in their network? Yeah, damn good proportion of you. Great. But ultimately, if you've got the card on your bench, if you've got it back in the lab, if you get it back to us, we'll put it on a real spectrum analyzer and actually have a look, see what's going on. It could be that the card hasn't actually gone faulty. It could be that you're operating the card in a mode, in a manner that is not recommended. Just because you can type in values into the settings for the card doesn't mean to say you're doing it correctly. Microtik trusts you to know what you are doing. They provide you the tools. They provide you with the power to be able to do these things, but ultimately it's up to you to be intelligent and knowledgeable enough to put the correct settings into the wireless card to make sure it functions optimally. I hope at the end of my talk you'll have a better idea of what those values are going to be and how you should set it up correctly. So you might think you want to set it up in a certain way. That's your theory. You want to run it at a certain transmitter power. You may have done the link calculations. You have a link budget. You know what your country's own internal regulatory transmitter power limits are. And you've now made sure that everything is all legit. You've got all the settings correct, but things still don't quite work as well as you expected. So what's happening? It could be that something has failed. It does happen. You ever seen those traditional graphs they draw of the failure rate over time, and it looks like a bell curve that the manufacturer will say that the majority of the failures will occur after so many years, but there will still be a small percentage that fail on day one. It happens, but the majority will fail at some time in the future. It could be that the card has not actually completely, totally failed. It could be that it's not as simple and as straightforward as that it just doesn't work. Those are easy to figure out because the link won't come up. And you change the card for a new one, it works beautiful. You have a broken, completely zero output transmitter. That's an easy one. But what if the transmitter is not actually transmitting at full power, it's transmitting low power? That starts to get a little bit more difficult to figure out. What if the transmitter is not just transmitting on the channel that you've set it to, but it's also generating what's called spurious transmissions all the way up and down the band, and is then affecting and causing interference to other co-located users in the spectrum band that you're using? These things are very, very difficult to figure out. So what I did, I used a calibrated Rohde & Schwarz spectrum analyzer with attenuators and just connected it to one of the chains at a time. It is quite possible that just one of the chains, one of the output feeds has failed, not one or all of them. You have to check them all. So if it's the net metal triple chain, you're going to have to test all three outputs. So I did that, and I also made sure that I put the other outputs onto a dummy load. A 50 ohm resistive load and that then made sure that even if it was accidentally transmitting some RF out of the other ports I wasn't testing, it wouldn't affect the results. So how about some of the lovely things that I've seen? Now, you've all seen the diagrams. For those who are interested in looking at this in deeper detail, you've looked at the diagrams of what a typical 802.11n or AC radio transmission shape should look like. Fairly flat at the top, with a little notch in the middle, fast rolling off sides, and then a slope down the sides further down. But what the hell is that thing going up at on the lower frequency end? The card has a built-in EEPROM chipset which stores a data table of what transmitter powers should be coming out of the card for which frequency. So something has gone wrong with this card because it is incorrectly setting the transmitter power at a higher level at one part of its transmission compared to the rest. Same again. It's gone a bit wonky. It's not flat anymore. Now that's going to cause, all these sort of shapes are going to cause errors within the radio transmission. You will look at the signal levels, and the actual number of dBms that you find in the status information in RouterOS will probably give quite a healthy signal strength level. But because you can't see the strange, weird shape that it's got, that's going to cause errors. You're going to get what's actually called a very high EVM, an error vector magnitude value. The actual higher data rates will not sync up, and it will only stay at the lower data rates. You'll never be able to get the thing to rise up to the higher modulation rates, because the errors become so great in being able to decode the constellation diagram of the QAM modulation system. Too many errors, it falls over and drops to a lower speed. What's happened here? Here is another card that the way in which the actual QAM, the quadrature amplitude modulation system, is generated is done from two subcarriers, which are then mixed together 90 degrees out of phase with each other. If that mixing process in the chipset fails and doesn't work correctly, you end up with a spurious RF radio carrier right slap in the middle. Even though that's a faulty transmission, you can see there's a notch in the middle. In that one, there is a notch in the middle. That's not a notch. That's actually radiating power in the very, very center of the frequency, which there should not be any carrier there. That should be no transmission at all. This one, the power amplifier, the PA, the power amplifier chip, the transistors that actually boost the transmitter power coming out of the Atheros chip, has failed. You can see that that is not as small a radio transmission as you would expect to see from the traditional diagrams you've seen. It certainly doesn't look as nice and shaped like that, with the flat sides or the slowly sloping off sides. That's going to cause a lot of interference to other users, or maybe even your own sectors and your own point-to-point links on adjacent channels, isn't it? It's spreading quite a long way to each side. If you look at a really, really much wider view, if we zoom out and look at the radio spectrum coming from a card, which is perfectly healthy, this is a good working card. It's a 5 gig transmission. We're looking at a 1 gigahertz span across the whole of the analyzer. I don't see any other radio transmissions coming from that card. That's a faulty one. So once again, that's going to be causing problems to co-located adjacent channel or anyone else in the same band as you. And the levels at which these are being transmitted at are, as you can see, 40 odd dB down. Some distance away from the site, those little spurious subcarriers will probably be undetectable. But if you're using the same site with other frequencies in the band, especially lower down than this one was on, that's going to cause you a lot of interference. If you're operating a 40 megahertz system, you have a main control channel on the main 20 megahertz channel that you've set the frequency to, and then you have an additional 20 megahertz channel as an extension channel. Very crudely, very simply, you're bonding two channels together to double the bandwidth, to double the throughput. But what's happened here is that when the chipset has generated the extension channel, it's at a completely different power level to the main control channel. They should be absolutely flat with each other, but it's not. It's actually gone and dropped it by about 3 dB. If I went into the router OS settings and I changed it from upper to lower, so as to move the extension channel to either be above or below the main control channel, well then the thing flips over and just looks the other way around. But it always has one higher than the other by about 3 dB, so that's not right either. Because then when you go to the higher data rates and you go to the higher MCS codes, and you're trying to go up to the 300 megabits per second data radio rates, you're never going to achieve it with as good a throughput as a working good quality card, because you're dropped by 3 dB in the extension channel. So those are some of the faults that you might be able to find. Now let's have a look at what happens when you set the actual transmitter power on the card and how you should be setting it correctly. You type a number in. You put 15 in, 15 dBm. You type the number 15 in. What you're going to get out? You're going to get 15 dBm out? Can you guess where this is going? You don't really know unless you measure it. And there's also some little tricks about tolerance. I'll show you a table, for example, that Atheros says about what power you put in and what you're actually going to get in reality. But there is a feature. When the AC chipsets came in, MikroTik wrote the wireless FP package to provide the AC drivers. But the way in which the power is displayed is slightly different. If it is running a traditional N chipset, then the two chains will add together to give you an extra 3 dB power. So it will say to you, for example, that one of the chains is 27 dBm, the other one is 27 dBm. In the status information, you have to add those two together to know that in reality it's actually genuinely putting into your antenna 30 dBm, because it's adding two chains together. And if we double the power from the two chains, we're doubling the power, that's a 3 dB increase. But that's not the case if you're running AC mode. The AC modes, the AC chipsets, if you set it to 27 dBm, it will automatically compensate for when you add the additional chains. So if you add a second chain by having an extension channel, it will display in the status information that it is still 27 dBm. But the reality is, it's actually now two lots of 24, making 27. So you need to bear that in mind when you are doing your regulatory EIRP calculations. So then we come down to one of the best chipset manufacturers that MikroTik's using, the Atheros, the Qualcomm Atheros chipsets. What do they actually say is their guaranteed manufacturer's output power? You notice, if you can see that, it says that they will guarantee that the chips will generate an output power that is within plus or minus 2 dB. In good old wet finger out there in the real world values, that's nearly-ish double. Plus or minus 2 dB is actually a 4 dB range, so it could be that you're getting out from your card 2 dB less than what you've set it to. Maybe that might help you with some of your links, so that when your regulatory engineer comes to visit you, you say, oh, I've taken into account that the card is running 2 dB down. And then he says, yeah, but I'm taking into account that it's running 2 dB up. But that straight away is telling you already that what you type in is not necessarily what you get. The other thing is that if you're going to measure the transmitter power, there's actually very, very limited amount of tools available. There aren't very, very good, high quality, low cost transmitter power meters. So the only way you're going to really, really know for sure what your transmitter power is and what your EIRP is out of the antenna is if you actually measure it with something that is trusted, calibrated and traceable back to a national standard. In the UK, the equipment can be calibrated back to a standard that's maintained by the National Physics Laboratory. I mean, in the States, it's NIST. So let's have a little question about making measurements and actually having a value. Which is the most accurate of the two? If I write down that the transmitter power is 23.4376, is that more accurate than 23.4? Put your hands up if you think that A is more accurate. Put your hands up if you think A is more accurate. And put your hands up if you think B is more accurate. The answer is you don't know. You don't know because we don't know what's called the uncertainty value is. What is the uncertainty? Uncertainty is a value which can be provided by a manufacturer of the test equipment to say, do you know, I don't really know exactly what value I'm measuring within a range of plus or minus so many dB. I know it's roughly this value, but it could be in error by plus or minus so many dB. This is a calibrated, accurate, I don't know. But that's the only thing you can do. So you're actually taking a piece of equipment to a laboratory and asking them to calibrate it and to tell you what is the uncertainty value, how much they think it is most likely to be in error by. And various equipment manufacturers will quote that. So I've been using a Rohde & Schwarz FSH 828, which goes up to 8 gigahertz. And it has some tools built into it for measuring power, which is cool, because one of the things about Wi-Fi, because ultimately that's what all this stuff is, I know we're using NV2, and it's a TDMA-based protocol, but ultimately it's still using the standard Atheros Wi-Fi chipsets. They're pulsed. They are not 100% duty cycle. They're roughly 50% duty cycle. So to measure the power of something that is only there for half the time is not really as straightforward as it first appears. So that luckily, Rohde & Schwarz, at enormous expense, have provided the tools there for me. So I can feed a NV2 TDMA-based transmission system into this, and it will tell me exactly how much power I'm feeding into it. But how accurate do I know it is? I can look it up. So even though the equipment has got a calibration certificate, Rohde & Schwarz states that if I'm making measurements at around 2.4 gigs, they believe that the equipment is likely to be better than 1 dB. So what they display on the screen will be within 1 dB of reality. But typically, most of the time, if it's been calibrated and adjusted correctly by the laboratory at the calibration house, you should be able to achieve an accuracy of 0.5 dB. So that's the uncertainty value. At 5 gigs, it goes up to double that. They say typically should be within 1 dB of what you've measured. So if you've got something that says, I've measured the value as 23.4376 dBm, because that's what it says on the screen, we now know that that's rubbish, that's stupid, because the uncertainty value is 1 dB. So really all we can say is 23. It's neither of those. So once again, I connected the equipment up and I had a look at seeing what was going on with transmitter powers. So I had a look at setting the card to 10 dBm. I entered in 10, and then I measured the power across the frequency band of 2.4 gigs from a typical MikroTik card, an R52HN. A good workhorse. It's proved to be very reliable. And what I've actually measured, it's within 1 dB. Remember the 1 dB in uncertainty of my measurement. So that is a measurement of within plus or minus 1 dB or so. So that's good. That means that if you operate that card across the 2.4 gigahertz band, it's going to get roughly the same amount of power across, no matter what frequency you use, it's going to output the same amount of power. What happens when we do it on 5 gigs? It looks more scary than it is because the scaling of that is quite detailed. It's going from 17 to 12. That's a 5 dBm range on the vertical axis. But across the 5 gigahertz Wi-Fi, the international 5 gigahertz spectrum, that's within plus or minus 2 dB. But it's not a flat line, is it? It's curved in a very strange and odd way. There's nothing wrong with that. It's perfectly normal. But remember what I said at the beginning, that what you get is not necessarily what you thought you were going to get. Now let's have a look what happens if I again use 2.4 gigs, but I change the transmitter power setting. Start from a very low value and go up to the whatever is the maximum card transmitter power, which I think in this case was 23 dBm. That's fine. That's still within spec. Don't forget, all the slides will be available on the MikroTik wiki, so you can get much better screenshots from this offline. Or no, online. The problem comes when you actually start to go down in power. So the previous ones, I stopped these measurements at 5 dBm. It's well within spec. Fairly flat line. But if you go down below 5 dBm, things start to go a little crazy. The reality is, if I draw it as a curve, that's not a nice diagonal straight line. It's not linear. It flattens out at the top, and it definitely flattens out at the bottom. That's because the information that the manufacturer has stored within the EEPROM chipset part of the Atheros chip, the electrically erasable PROM, says you can't go more than that power, whatever it is, 23 dBm, because that's all the card is being manufactured to generate, is 23 dBm. If you try and push the electronics beyond 23 dBm, it will fail the ETSI technical parameters, and then it will lose its certification as a wireless card in the States under the FCC regulations, and here in Europe for the CE, the directives. So they have forcibly stopped you. So even though you can type in a higher value, you're not going to get it. And likewise at the bottom end, you can type in very, very low values. For example, I typed in minus 30. Did I get minus 30? No, I got minus 2, because it had already flattened out. I'd already got to the bottom of the curve, and the Atheros Electronics has said, if you go any lower than that, it will cause problems with our certification. You are now taking the card outside of its design parameters. And RouterOS and MikroTik as a company are actually taking that information that Atheros is providing them in that PROM chip and saying, well, if that's what you're telling us that this card can do, we'll believe you. And that's why you get this strange, weird shape. But the RouterOS system does allow you to type in some crazy numbers, but that's not necessarily going to give you the right output. So if you're running a very, very high antenna gain on a point-to-point link, maybe 30 dBi gain, in the United Kingdom, the maximum allowed number of power, the maximum power is 36 dBm. So with a 30 dBi antenna, I need to set the transmitter power to 6 dBm. I can do that because luckily, if I set it to 6 dBm, I will get 6 dBm. So that means I can sleep at night and know that I'm not going to be over power. If you was to put a much higher gain antenna on such a card, and you did the calculations and it came out and said, I've worked out I need to put in 2 dBm, you can type it in, but you're not going to get it. You'll get more than that, because it's already limited and flattened out at the bottom. But you know, if you want to pay thousands of dollars for a card, you can get a much linear range, you can get a much greater amount of performance and much flatter line, and it'll be, every single card will come off the production line and having been calibrated and tested and come with a certificate. But that's not the kind of money that you guys are paying, is it? $40 or $50, $60 for a card, you're getting everything within the quoted specification from the manufacturer. There's no lies being told here, you just need to dig out the information and find it. Okay, another little thing that I'd like to touch on. 2.4 gigs. Can I have some hands up? How many of you guys are deploying enterprise, educationally, in buildings, Wi-Fi on 2.4 gigs? Putting Wi-Fi in for customers, large enterprise deployments perhaps. Following Leo's talk this morning about using Capsman, very easy to deploy Wi-Fi, but you have to go back to each of the radios and set them to the correct radio channel so they don't overlap. You can't very easily maintain a reliable network with a single channel architecture. You can't have the whole site on channel 1 or the whole site on channel 6. They'll all interfere with each other. So we know these plans by now, don't we, guys? We've seen the books, we've seen the movie. We make sure that we deploy our access points on 3 non-overlapping radio channels. 1, 6, 11. We know that, don't we? But are they actually non-overlapping? What I've done here is I've got 3 access points. They are overlapping. At very low down levels, I admit, about 30 dB down, they are definitely overlapping with each other. There's no trickery in this. So if you co-locate 3 access points in the same room, they're going to be seeing each other. Even though you have put them on 1, 6 and 11, you will find that there will be cross interference between 1 and 6 and also between 6 and 11. The only ones that you can really truly have has no interference at all is if you put it on 1 and 11. Makes it pretty damn hard though to deploy just 2 channels in a building, doesn't it? But just bear that in mind, okay? They are actually still overlapping. So the diagrams, that's a little bit fairyland. Fairyland says they are not overlapping at all. But the reality is that they still do. You need to put some distance between the channels, both physically in meters across the ground, or by putting building attenuation in the way. You need to get the overlap section right down so that they overlap at very, very low levels indeed, maybe at around 50, 60 dB down. On 5 gigs, if you are co-locating on 5 gigs, the problem has still not gone away, even though there's approximately 19 odd channels available in Europe for deploying Wi-Fi on 5 gigs. And the channels are now 4 channels apart because the channel numbering is 5 megahertz. So that's why it goes 36, 40, 44. They're actually jumping in 4 channels at a time, which is giving us a 20 megahertz channel step. If you put 2 access points in the same location on, say, 36 and 40, they'll interfere with each other. So you need to make sure that you move the channels further away. So in the same room, you could deploy 36 and 44. So put a 20 megahertz gap in between the upper edge and the lower edge so that there's no overlap. Same thing applies if you're doing sectorial deployments. 3 sectors on a mast, you can't put them radiating on 3 adjacent channels. They will overlap, they will interfere, and you will get slower data rates. The other thing is, I don't know if that can be seen. Yes, it can. Good. Pigtails. You've got the blue MikroTik ones that are provided with antennas like the MANT 30, and there's loads of other pigtails available. Quite low loss usually, less than a dB loss, but the actual loss is not statically flat right across the band. It has actually got some resonances built into it due to reflections that occur between the two ends of the pigtail connections. You will get radio waves bouncing backwards and forwards, causing various reflections, and there's also the property of the length of the cable may be related to some fractional part of a wavelength. You will always get a curve. And again, it is actually going up and down by about plus or minus half a dB. That's another dB of uncertainty thrown in. So when you're trying to calculate the EIRP, how do you know what you're really doing? There's a lot, yes, there is some guesswork in this, but try not to get too paranoid about every single last decibel. To be honest, if your point-to-point link can't lose a few dB without it failing, you've done your job wrong in the first place. Because we all know about fade margins. We know that signals, the longer the link, the longer the distance of the link, the more fade there will be. You need to make sure you build in a budget, enough margin, so that your links stay up. So don't go chasing that one last dB. It really is not going to make any difference to the ultimate quality, the performance of the link. Okay, the last thing I'm going to mention is that what I've discovered from some of our customers is there's some confusion about the newer cards and the newer chipsets and recent versions of Router OS, and it's also mentioned in the wiki, is that you have to set the transmit power mode to all rates fixed. You don't actually have to set it to all rates fixed. You can set it to default. And there's a big difference between the way they work. If you leave it set at default, then it will totally take in the regulatory settings that you've inputted, and hopefully you have put in a country and set it to regulatory domain. It will take that information from the chip as to what transmitter powers and frequencies are allowed in your country, and it will make sure that it performs correctly with the maximum transmitter power and the frequencies, but also there is another section built into the chipset that if you set it to default, it makes sure that when you go to the higher modulation data rates, it brings the transmitter power down. It forcibly reduces the power. So even though you have programmed in plus 23, you may find you're not getting 23, you could be getting 17. Because the card manufacturer has said for us to maintain compliance, to meet the specification provided by ETSI, we need to bring the transmitter power down to stop the transmission widening up and spreading across into the adjacent channels, which would then mean that the card would then fail the CE certification and wouldn't be allowed to be sold or distributed in Europe. Same rules would apply in the States under the FCC regulations. So it takes that into account when you use default. If you use all rates fixed, that overrides that, and it says if you've typed in 20, you're going to get 20. If you type in 23, you will get 23, regardless of what modulation data rate it has risen up to. That then means that the ETSI spectral mask, you can find this in a very boring long technical document on ETSI's website, but there is a spectral mask that all these transmissions must exactly fit into. Basically, if it's a 20 meg transmission, it's supposed to fit inside a 20 megahertz channel and not spread out into the adjacent channels. But you can see it still does, and they allow it to have these shoulders or these skirts that spread out slightly from the center of the channel. That's allowed. You wouldn't be able to get the higher data rates if it didn't. So what's going to happen if I start increasing the transmitter power? I've set a card to all rates fixed. It's an R52NM, and I'm going to increase the transmitter power by 2 dB steps. So at 15 dBm, life is good. It's well within the spec of the card. I'm actually using Traffic Generator to artificially make it transmit broadcast traffic so as to push the data rate up to the highest data rates. So the card is nice and easily fits within the ETSI spectral mask and would therefore comply. We now start increasing the transmitter power. Oh dear. And that's what's actually happening now. You don't know that it's happening. You can't see that it's happening, but I can tell you that it is. If you use all rates fixed, and you use the higher transmitter powers, where normally, at the higher data rates, it would reduce the transmitter power automatically for you, you've overridden it, you've forced it not to do that, your channels will spread a lot further than perhaps you were thinking that they were. So there you go. There are still a couple of places left on my MTCWE training course next week. Quick bit of sales. I've got 2 seats left on the MTCWE next week. If you want to learn a bit more about wireless and get more goodies out of my brain, feel free to be trained by me next week. If you come to me, I'll even give you a special discount. Included within the MTCWE training is a free net metal triple chain, which we'll take away with you because it saves me taking it back on my aeroplane because they're heavy. So thank you very much. You can now see that you don't always get what you wanted.